Parallel wiring is another method of connecting electrical devices. Parallel wiring means that the devices are connected in such a way that the same voltage is applied across each device. Here we show two resistors connected in parallel between the terminals of a battery. This picture is drawn as to emphasize that the entire voltage of the battery is applied across each resistor. Actually, parallel connections are rarely drawn in this manner. Instead, they are drawn as shown here, where the dots indicate the points where the wires for the two branches are joined together. The figures look different, but are equivalent representations of the same circuit. Here we see that the current from the battery splits at the junction, so that some of the current goes through the first resistor and the rest through the other. The amount of current through each depends on the value of each resistor. The current then recombines, so that the current going back into the negative terminal of the battery is equal to that coming out of the positive terminal. This is in accordance with the conservation of charge. Parallel wiring is very common. For example, when an electrical appliance is plugged into a wall socket, the appliance is connected in parallel with the other appliances, as we see here, where the entire voltage of 120 volts is applied across each one of the devices, the television, the stereo, and the light bulb when the switch is turned on. The presence of the unused socket, or the other devices that are turned off, does not affect the operation of those that are turned on. Moreover, if the current in one device is interrupted, perhaps by an opened switch or a broken wire, the current in the other devices is not interrupted. In contrast, if household appliances were connected in series, there would be no current through any appliance if the current in the circuit were halted at any point. When two resistors are connected in parallel, each receives current from the battery as if the other were not present. Therefore, the two resistors together, in parallel, draw more current from the battery than does either resistor on its own. According to the definition of resistance, R equals V divided by I, a larger current implies a smaller resistance. Thus, the two parallel resistors have a single equivalent resistance that is smaller than either on its own. Here, the water flow analogy provides additional insight into this important feature of parallel wiring. Here we show two sections of a pipe that have the same length that are connected in parallel with a pump. A different configuration can be constructed that has the same flow with the same pump pressure, in which two sections have been replaced with a single pipe of the same length, whose cross-sectional area equals the combined cross-sectional areas of the two. The pump, which is analogous to a voltage source, can push more water per second, which is analogous to current, through the wider pipe, which is analogous to a wider wire, than it can through either of the narrower pipes. In effect, the wider pipe offers less resistance to the flow of water than either of the narrower pipes offers individually. In analogy to the water pipes, it is possible to replace a parallel combination of resistors with an equivalent resistor that results in the same total current for a given voltage as the original combination. To determine the equivalent resistance for the two resistors shown here, note that the total current I from the battery is the sum of I1 and I2, where I1 is the current through resistor R1 and I2 is the current through resistor R2, or I equals I1 plus I2. Since the same voltage V is applied across each resistor, the definition of resistance, or Ohm's law, indicates that I1 equals V divided by R1 and I2 equals V divided by R2. Therefore, I1 plus I2 equals V divided by R1 plus V divided by R2, which equals V times 1 divided by R1 plus 1 divided by R2, which equals V times 1 over Rp, where Rp is the equivalent parallel resistance. Finally, 1 over Rp equals 1 over R1 plus 1 over R2, or the reciprocal of the equivalent parallel resistance is the sum of the reciprocals of the individual resistors. In the case of n resistors connected in parallel, as shown here, we have 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. We could write this more compactly using summation notation as 1 over Rp equals the sum as I goes from 1 to n of 1 over Ri. In a parallel combination of resistances, it is the smallest resistance that has the largest impact in determining the equivalent resistance. In fact, if one resistance approaches 0, then according to this equation, the equivalent resistance also approaches 0. In such a case, the near zero resistance is said to short out the other resistances by providing a near zero resistance path for the current to follow as a shortcut around the other resistances. We conclude with a final comment on power. In general, the total power delivered to any number of resistors wired in parallel is equal to the power delivered to the single equivalent parallel resistor. The same is true for resistors in series. The total power delivered to any number of resistors wired in series is equal to the power delivered to the single equivalent series resistor.